Dang it. Ah, man. Oh, well. Understandable. No, well, okay, so what this means is that the rate of, the instantaneous rate of change of the position is it stopped going up at this point.
I'm just saying because you do the same thing this time, you do the derivative and then plug in that.
Right, if we want to find the velocity at a time, you calculate the velocity at an arbitrary time, and then just plug in the time you're interested in. Yeah.
I thought instantaneous velocity was the velocity at a particular time.
Yes.
So, okay.
The velocity at time
Yes.
at time 3. Uh-huh.
So then why is it for C? Why is it not? Why is it not 0?
Well, part C is what's the instantaneous velocity at time t equal to 5 for me? So at time t equals to 5, I calculate v of 5. I mean, what's happening here, I mean, I can draw a picture. At time equals 0, s is equal, let's think s is vertical distance, okay? So at time equal to 0, it's down here. And then, I don't know, maybe it's probably a kitten, you know? And then, like, somebody throws it up into the air. It's a cat. Kit.
Why does it have a tail?
Kids can have tails. Let's see here. No? So the point is, what comes up must come down. That's what this formula actually says. What we found is that up here at t equals to 3, you have v of 3 is equal to 0, which reveals the fact that s is not changing. It's the top of the flight. Oop. And then at 5, it's probably down here somewhere, right? So I would expect that v of 5 is negative because it's going down. In fact, v of 5 is what? It's 96. Oh, I'm sorry. 96 minus 32 times 5, or 96 minus 160. 96 minus 160, I think, is 64. Yeah, 64. Minus 64, though, right? Am I right? And then the units here actually are feet per second, but you don't lose. I only take points off for units when I teach a physics course, so you're safe. So yeah, minus 64. So of course the ball is falling, right? When will the ball hit the ground? That's not a calculus question, that's an algebra question. So if s equals to 0 is the ground, to find when it hits the ground, we just solve s equals to 0. But s is equal to 96 minus 16t squared. I think I lost a t, right? And so you're solving that equals to 0. Well, that's a quadratic equation, and it's kind of a simple one, too, because that's t times 96 minus 16t equals to 0. So that has two solutions, right? T equals to 0 is the first solution. T1 equal to 0, and also what? 96 minus 16t equals to 0, which gives us what? 96 is equal to 16t, which gives me my second solution, T2, 96 over 16. Also popularly known as 6. So 1 second after it's falling at a rate of minus 64 feet per second, it hits the ground. Yeah, 3 seconds up, 3 seconds down. Of course, you could have doubled that if you have a good intuition about what motion looks like physically. There's a symmetry between going up and coming down, right? So you're like, well, if I understand how this works, can I just double the time at the top? Yeah, if it's ordinary constant acceleration motion, that's true. For other more exotic formulas, it wouldn't be true. Like if I had a cubic dependence on time for the position. Question, yeah?
On homework 4, have you gone over like number 14 and 15 yet? How to solve this?
I think so. Let's see here. Let me look into it. 14 and 15. Ah, yes. I'd be happy to do one of those for you. We actually did a problem kind of like this. It was my second example right after the product rule last class. Remember, I said f of 2 is blah, f prime of 2 is blah, and we worked out f times g prime of 2 in terms of the product rule symbolically. But here, if I work one of these, I think you'll see how to do the other one. So this is homework 4, number 14. So we have h of x is defined to be x squared plus 7 times g of x. And let's see here, what else are we given? We're given that, why has he got stuff about f? There's no f here. It's funny. Okay, whatever. I mean, f of 1 is equal to 2. F prime of 1 is equal to minus 1. There's a bear in the woods named George. It's just as relevant to this problem. I don't know, like, who cares? G of 1 is equal to minus 2. G prime of 1 is equal to 3. Find h prime of 1. This may be some sort of perverse attack on people who assume this problem is the same as the example I worked in the previous class. I don't know. I'm not sure why the extra information about f is there, but whatever. Let's not be distracted by it. What's h prime of x? What's d dx of h? It is the derivative with respect to x of a product of x squared plus 7 times g of x, right? How do we differentiate a product? Product rule, right? So this is the derivative with respect to x of 2x of x squared plus 7 times g of x plus x squared plus 7 times the derivative with respect to x of g of x. And I have to think symbolically here because I don't have a formula for g, right? So I mean, I have to be content with an expression such as I'm writing. And of course, this simplifies. This is just 2x, g of x, plus x squared plus 7 times g prime of x. And there you go. For arbitrary x, that's the best I can do. That's the answer. That's the derivative function for h, right? But what's this question ask us to do? I have to find h prime of 1. So what do I do with what I just found? I just do what? Just plug in 1, right? So h prime of 1 is 2 times 1 times g of 1 plus parentheses 1 squared plus 7 close parentheses times g prime of 1. Which is really just what? 2, what's g of 1? Minus 2, right? That was given. Plus what? 1 plus 7 is 8. G prime of 1 was what? 3. So there you have it. The answer is 24 minus 4. It's 20, for mine anyway. So the way that's number 14, and the end, number 15 is done almost the same way. Okay. Yep.
Can you explain how to do 6 on the table?
Homework 4, number 6. Number 6, you're supposed to find the limit. Oh, this is actually really neat. This will actually take us all of 30 seconds. The limit as h goes to 0 of 1 plus h quantity cubed minus 1 over h. So this is a backwards problem. So what you got to do is look at this as the difference quotient of something. This is the limit as h goes to 0 of f of 1 plus h minus f of 1 divided by h. We've actually already seen this today. This was f of x equals to what? It was in the case-wise function. It was the thing that the Star Trek detractor made me use a simpler formula for. I guess I should learn your name, but it's more fun to refer to you by your abject ignorance of Star Trek. How dare you? How dare you? How dare you? So if that's the difference quotient for f of x cubed, f of x equals x cubed at x equals to 1, right? So this is, in fact, just f prime of 1. But that's 3x squared setting x equals to 1, which is otherwise known as 3. So the game that's played here is to work backwards from a difference quotient to a power rule. It's an inverse problem. These are really, really hard if you don't look at it that way. Yeah.
For number 8, when it says the tangent line and then it asks for the normal line, what is it?
Oh, great. The normal line, so if this is my function, like this, if this is the tangent line like so, the normal line, it's fine if you got to go. The normal line is like this, I got to stop. It's like that. It's just it's perpendicular.
Okay.
It has negative the reciprocal of the slope of the tangent line. You can go ahead. We got to stop. So you can cut it off. Thanks.